Stability analysis of a series RLC circuit, that is called second order circuit. Okay, by using this circuit, series RLC circuit, we have to find the transfer function V naught of S by Vi of S. V naught of S is called voltage across the capacitor and Vi of S is called input voltage. So V naught of S by Vi of S, after finding the V naught of S by Vi of S, so we will get one transfer function. By using the transfer function, we have to find stability analysis theoretically by using semi-logarithm graph. So by semi-logarithm graph, we have to find phase crossover frequency and gain crossover frequency, and also gain margin and phase margin. Okay, if phase crossover frequency omega pc is greater than omega gc, the system is called stable. Omega pc is greater than omega gc, phase crossover frequency is greater than gain crossover frequency, the system is said to be stable. Omega pc is less than omega gc, that is called phase crossover frequency is less than gain crossover frequency, the system is said to be unstable. And if omega pc is equal to omega gc, that is called marginally stable. Phase crossover frequency is equal to gain crossover frequency, the system is said to be marginally stable. So by using piecewise, we have to find the uh, omega pc, that is called phase crossover frequency, and omega gc, gain crossover frequency for second order circuit. So in this second order, in this piecewise, so this is called VAC. So VAC, voltage VAC, so is equal to 20 volts. Okay, change the display both name and value. So this indicator like this, and AC magnitude is equal to 20 volts. So whatever it may be, the voltage, so we will get the transfer function V naught of S by Vi of S. So take one voltage source VAC and place here, and take one resistor from the PSpice library, place here, and similarly inductor. Okay, and capacitor, connect all resistors, all elements in like series. Okay, RLC are connected like series fashion, and also one ground is connected in this way. Okay, so go to markers, and mark advanced, and take VDB and also V phase and place on this across the capacitor. Okay, across the capacitor, this is called V phase and this is called VDB. So place across the capacitor. This is called second ground terminal, and this is called capacitor one terminal. So that is nothing but across the capacitor one V phase, that's called phase plot, and VDB, that is called magnitude plot. Okay, so if you want to display the color of V phase, go to here, this none, the color marker, select this color, and then phase plot will be displayed in this color. Same way here also. So if you want to display the color, select and then simulate. Okay, after this, go to analysis, and go to analysis, setup, AC sweep analysis. Frequency domain analysis is nothing but is related to the AC. That's why AC sweep analysis. Enable AC sweep analysis and press AC sweep analysis, and press here. There are three different types of options. One is called linear, second one is called octave, third one is called decade. So from this, select decade. So our graph will be, our semi-logarithm graph will be displayed with respect to dB by decay. So 20 dB by decay decreases. So if you want to display the graph in the form of decay, okay, so we have to select this icon, decade, and also starting frequency 10 Hz, ending frequency is called 10,000 Hz according to our graph. According to our values, RLC values, we have to check the ending frequency. Okay, and then press OK, and then simulate, close, and simulate. Okay, simulate, and then new pop-up is appear like this. So this is our graph, semi-logarithm graph. So for this, the red color is called VDP, means magnitude plot. This is called magnitude plot. The red color is called magnitude plot, and this green color is called phase plot. Okay, so this is called phase plot. This is called magnitude plot. Red color is called magnitude plot, and this green color is called phase plot. Fine. And then, if you want to separate the two waveforms in same graph by changing the y-axis scale, so okay. So if you want to display this two different scale in one graph, select this VDB and press Ctrl X and go to plot and add y-axis and then Ctrl V. Okay, so then two graphs are separated on y-axis, but x-axis same. X-axis common for magnitude plot and phase plot, that is called frequency. X-axis is common for both the magnitude and phase plot is same. That's why no changes in x-axis. So only changes in y-axis, that is called, one is a phase plot, but that is means degrees. You will get degrees. Here degrees means first one is called this degrees means 0 degrees, 90 degrees, 180 degrees, like this. So I display like this. So VP, this color is called green color and is represented here 1. Okay, phase plot. So that is nothing but the 1 is related to the phase plot. Okay, this is called phase plot. Understood? So then here 1 is nothing but here also 1. Okay, then here 0 dB, minus 0 dB, it is displayed minus 0 dB. Okay, minus 0 degrees. Phase plot is nothing but degrees. Okay, one is called corresponding to degrees. Minus 0 degrees, minus 50 degrees, minus 100 degrees, minus 150 degrees, minus 200 degrees. This is the scale of y-axis for corresponding to phase plot. Similarly, this is a second one. Here this 2 is there, that means here 2. This second one is nothing but dB plot, that is called magnitude plot. Here 100 decibels, 0 decibels, 0 dB, minus 100 dB, minus 200 dB. So like this, two y-axis are separated. I mean, y-axis is separated. One is phase plot and one is called magnitude plot. This is called phase plot. One is called phase plot. Minus 0 degrees, minus 50, minus 100. Okay, degrees like this. This is a phase plot, and then this is called magnitude plot. 100 degrees, 100 decibels, 0 dB, and minus 100 dB, minus 200. Like this, the y-axis is separated. And then here, how to find the gain margin and also gain crossover frequency. So gain crossover frequency is nothing but the gain margin, that is called gain magnitude plot is crossing the 0 dB line. The corresponding line is called where it is crossing the line is called gain crossover frequency. Here this is called dB. Okay, so enable toggle cursor, and this is called dB, means magnitude plot. Okay, red color is called magnitude plot. This is called magnitude plot. The magnitude plot crossing. Okay, so this when the probe is moving like this, the display changes. This is called probe output. Probe cursor changes. Okay, when the probe changes like this, when the cursor moving in this way, this probe cursor display different values of x-axis and y-axis. So when it is crossed the 0 dB, that corresponding frequency is called gain crossover frequency. If moving like this is called okay, it's moving like this, it is a display x-axis and y-axis. Here this line is called 0 dB line. Understood? This line indicated as a 0 dB line. This line is called a 0 dB line. Okay, this line, this is called 0 dB line. Like this, the line is known as a 0 dB line. Okay, corresponding 0 dB line frequency is called 0 dB line. That means magnitude plot crossing 0 dB line, corresponding frequency is called our green crossover frequency. Okay. Then this corresponding line is nothing but is the line. So from here to 22.414 kilohertz, the corresponding line, this on x-axis, this is called our frequency, green crossover frequency. Okay, this is our gain crossover frequency. On x-axis, that is called 22.414. This is our omega GC gain crossover frequency. Okay, so like this we have to represent on Bode plot practically by using PSpice green crossover frequency. We have to find green crossover frequency in this way. Okay, similarly, and then we have to find phase crossover frequency. Phase crossover frequency is nothing but phase line, that is called phase plot. This is called phase plot. That is nothing but this is one. This is one is called phase plot. When phase plot, so select this phase plot and enable toggle cursor like this. Select this phase plot and is moving. Cursor is moving like this. When the cursor moving like this, and this probe cursor display x-axis and y-axis. That is called x-axis is called frequency, y-axis is called decrease. Okay, in this way. Here phase crossover frequency is nothing but phase plot crossing the minus 180 degrees line. Okay, where the phase plot crossing the minus 180 degrees line is called phase crossover frequency. Okay, so select this one phase plot and enable toggle cursor and move cursor on this. Okay, so this here minus 174 degrees y-axis, this is called x-axis, and here minus 174 degrees. That means we require minus 180 degrees, na? So minus 180 degrees line, we need minus 180 degrees line. So this line is called minus 180 degrees. So minus 179.962. So 240, approximately 240 kilohertz. Okay, 240 kilohertz. This line, this is called a phase crossover frequency. Understood? So phase crossover frequency, this phase crossover frequency changes. Minus 179.9 approximately is equal to 179.99 means 180 degrees. So here frequency is called 1 megahertz. So it's very, very high. That maybe theoretically we will get infinity. Otherwise, there's a maximum value 17752 kilohertz. So here this is called phase crossover frequency. Okay, phase crossover frequency. This is called phase crossover frequency, and corresponding 0 dB line crossing, that is called gain crossover frequency. Here phase crossover frequency is greater than gain crossover frequency. That's why this system is stable. Okay, so where we have to find the how to find the green crossover phase crossover frequency means 180 degrees line. When it is touching the 180 degrees line from here onwards, this line is called 180 degrees line. Here exactly we will get minus 179.99. The corresponding frequency is called 752 and 123 kilohertz. That is very, very high. Okay, corresponding this frequency is called our phase crossover frequency. Like this, we have to find phase crossover frequency and gain crossover frequency. Understood? Similar way, and then next, how to find the gain margin? How to find gain margin means from 180 degrees line, where it is touching. Okay, this is called a phase plot. This phase plot, this is our minus 179.99. Okay, this is our minus 180 degrees line. Understood? Here minus 180 degrees. Uh, Here this is the frequency 857 or 753 approximately you will get lines. So minus 179 point. So this phase plot is touch the minus 180 degrees line here. So corresponding line when we are extending the line, okay. So like this fashion. So minus 179.9 means we have 180 degrees. When you are extending the line like this line touches the gain margin line, gain magnitude plot line. Understood? So this line. So that means here 0 dB to this line and this touch line, this distance is called gain margin. Okay. So this line, the corresponding line 0 dB line. Okay, here to 0 dB line to, and then this is called our gain margin. This is our gain margin. This length here is called gain margin. So in this way we have to find practically gain margin. Similarly, phase margin. So phase margin is almost to zero because of there is no margin between 180 degrees line and this phase. Okay, that's why it is phase margin zero and phase crossover frequency. Phase crossover frequency is almost infinity and gain margin is not exist or zero. So like this, we have to find gain margin and phase margin uh, practically by using this Bode plot. Okay, this is about frequency domain analysis. Here omega PC is greater than omega GC. Omega PC, this is called omega PC, and 0 dB line here, this is called omega GC, grain crossover frequency. By drawing the line, this is called 0 dB line, and this is called phase plot. The crossing point, this is called crossing point. When corresponding this on x-axis is called this is our this is our uh, gain crossover frequency. This is a phase crossover frequency. Phase crossover frequency is greater than gain crossover frequency. That's why this system is stable. Okay. So in this way we have to find gain margin and phase margin and stability analysis of a system. Okay. So omega PC is greater than omega GC. That's why this system is stable. Omega PC is less than omega GC, unstable. If VG is equal, marginally stable. And so corresponding 0 dB line is called gain crossover frequency. Minus 180 degrees line is called phase crossover frequency. So by extending the line in this way, so we will get touches the phase margin line, and then this length is called 0 dB line to this length is called gain margin. And here this is called negative side. That's why gain margin we will get negative. Phase margin is also 0. So in this way we have to execute this experiment. Okay. Frequency domain analysis of a series RLC circuit.